My name is Rick Steiner. I am one of the contributors to SysML, the system modeling language, from its inception through its current state of development in 2014. And we're currently working on version 1.5. During the progress of the development of SysML, one of the things that came out as a interesting educational aid was the concept of the four pillars of SysML. I cannot claim credit for coining the term the four pillars. That belongs to Chris Coburn, who was one of the co-leaders of the SysML development team at the time. And he coined that term based on the four basic principles that I and some of the other contributors related to him that system engineers really need to be able to do with any kind of system model. And from his perception and coining of that term for the four pillars, I developed an initial primitive example that I did in Visio. And over time, a lot of people have used that example to great extent, and I see the icons for the four pillars appearing all over the place. Well, those particular early diagrams have gotten a little long in the tooth, a little tired. The graphics were never very good to start with, so I've rebuilt the four pillars charts using Magic Draw as the source of the model that built the diagrams, and did a little post-processing in Acrobat, in Illustrator to make them look a little bit nicer. And I thought it was important for me to just record, finally, my interpretation of the four pillars. I've given this pitch many, many times, and I thought it would just be good to record it for posterity. And maybe it would be useful to a broader audience that way. So here are the four pillars of SysML, presented in a very compact way, showing the basic concepts of SysML and how they relate together. The four pillars of SysML are structure, behavior, requirements, and parametrics. These are the four basic things that system engineers have to deal with on a regular basis when talking about systems, and the system modeling language was built to be able to support. And so what I'm going to be doing is walking you through these four basic areas and showing how SysML represents these basic areas and concepts, and then how they can be cross-connected together. So we'll start off with structure. SysML addresses structure in two basic ways. The atomic unit of structure in SysML is called a block. A block is different than a class in UML, as it has some extensions to it, but really is meant to represent something that you would specify in your system that would actually provide some value to that system. And that has to have certain characteristics, it has to have certain values, and it has to have a very strong sense of a hierarchy, in other words, a parts list. So SysML strengthened the idea of a class structure or composite structures that we got from UML into this system engineering paradigm, and we settled on the term block, as in a building block. Now, the first kind of concept I want to talk about is the concept of definition here. This first diagram is called a BDD, or block definition diagram, and what you see on here is showing, you're seeing a number of different blocks. In particular, we've taken this example is about a anti-lock braking system, and the block in the center and the upper part there is an anti-lock controller. The anti-lock controller, as shown here, is composed of two parts. It's composed of D1 and M1. D1 happens to be a traction detector, as shown in the diagram, and M1 happens to be a brake modulator. composition is shown by the black diamond kind of relationship. There's another relationship shown in this diagram which is also quite interesting, and that is the white triangle relationship, which is one of generalization or specialization. In this case, you can see that the traction detector, the block traction detector, is a kind of electronic processor, and that the brake modulator is a kind of electrohydraulic valve. That's what the white triangle really means. You can also notice through the naming conventions used here, the namespace, that the electronic processor resides in a library which is actually external to the model that we're developing here, as is the electrohydraulic valve. What that allows me to do is say what the standard properties are for electronic processors, such as the need to have a certain clock rate, a certain memory size, or the fact that it even has a clock rate or memory size at all. Likewise, there may be some generic characteristics of electrohydraulic valves. And by saying that through this relationship that a traction detector is a kind of electronic processor, it will automatically inherit those basic characteristics or the placeholders for those basic characteristics, so that I can then tailor that to my specific need here. And in doing that, I don't forget something. And it also lets me have a library, maybe many electronic processors, and maybe pick one that will fit in this kind of design. Now, recognize that I've told you about what an analog controller is composed of. I've not told you about how the parts of the analog controller are connected together. For that, we need a different kind of diagram. We need a diagram of usage. Now, in a structural sense, the diagram of usage is called an internal block diagram. It's called that because it's basically looking inside the block analog controller. In this case, the IBD shown there, the diagram frame represents the analog controller, as if you've taken the analog controller on the BDD and you've kind of expanded it or blown it, zoomed out, zoomed into it to see what is going on inside. And here inside the analog controller, you still see D1, which is a traction detector. You still see M1, which is a brake modulator. But in this particular case, you also see that they are connected together with a connector C2, and that the D1 and M1 have ports on them that allow things to flow and actually describe an interface between those two parts. And that's a very important aspect to how we look at systems and their connections. In fact, for most people, most systems engineers in particular, when they are used to thinking about system block diagrams, IBDs are the kind of diagrams they're used to thinking about. They want to see what the various parts are inside the particular system. They want to see how they're connected together, and to some degree on an IBD they'll be able to see what kind of things are flowing around the system. With that said, now about structure, we have this complementary concept of definition and use that also can appear in other areas besides structure. Now let's move on to behavior. One way that behavior can be represented in SysML, we get this directly from UML, is the idea of an interaction or a sequence diagram. Sequence diagrams will be able to lay elements of structure onto a set of what are called lifelines, these dashed lines that go down the page when you're looking at a sequence diagram. And you can see D1 and M1 once again at the top of the page, and these lifelines running down the page. But what is really important to show, what a sequence diagram is really for, is showing the messages or signals or operation calls that might go back and forth between these two particular pieces of structure, or as many as you may want. You can have an arbitrary number of lifelines on a sequence diagram. So you can see that they could get a little bit messy. They also are showing when different operations within these particular structural elements, when those operations are enabled or when they're not. They show also when a signal is sent and when a return comes back. So, but what they're not showing is what's going on in any depth inside those elements of structure, inside those parts. You really can't tell what's happening inside M1 or D1 in this case. You can only see what's going back and forth between them. Another way that behavior can be represented in SysML, we also get from UML, and that is the use of a state machine. State machines have been around for quite a while. They are a very respected way of representing behavior. They represent the behavior of a particular piece of structure, usually of a block. And the block can be in several states, and the states can have substates. The state machine concept within SysML complies with Horel hierarchical state charts. In this case, now we're showing the state of a part of the system that we're calling tire traction. And it's showing the tire can be in a gripping state or a slipping state, assuming that it starts in a gripping state, and then if traction is lost, it goes into a slipping state, and if it's regained, it comes back. Now there's many ways that the state machine can invoke various behaviors based on a transition between states, or activities or things going to happen while it's in a particular state, etc. This is a very well structured and well understood kind of way of representing modeling behavior, very familiar to most of the software code generation tools, and it's a pretty helpful way of designing systems. But there are times when we really don't know which block you want to have exhibit this kind of behavior, in which case you might say that it's the highest level system, or you might want to have a different way of thinking about behavior which isn't really tied to a particular block. Hence we have something called the activity diagram, which is really a derivative of what was formerly known as functional flow diagrams. This is really showing no structure whatsoever. The last two diagrams have had some element of structure on them, and then you lay behavior on top of them. The activity diagram kind of flips that around and says, well, I'm going to talk about unconstrained behavior, and then eventually I can lay some structure on top of it if I need to. But in this case, I'm showing two actions, the round-cornered boxes on the activity diagram, action A1 and action A2. Action A1, they're both called behavior actions. You can understand that from the little rake symbol, and also from the fact that their naming convention has a colon in it between the name A1 and then the name of the activity that is invoked by the call behavior action, in this case, detect loss of traction. You see that there's a start state, there's a starting point, there's an ending point. The dashed lines are representing control flow. This solid line is representing object flow, or data flow, if you will, and that's flow between the two actions. And this is a very handy way of talking about unconstrained behavior, which can be very helpful early in the concept definition phase when you really don't know exactly what pieces of structure you're dealing with, and is also very useful for starting to refine use cases and functional requirements. Now we go into the requirements pillar. SysML is not unique in that it handles requirements, but it is unique in that it's based on UML, which has no concept of requirements as a first-class model element. So in SysML, we had to do something to accommodate requirements. What SysML has at this point in time is a model element that is not a classifier, but does have two fundamental attributes. It has an ID, which can be a string or whatever you want it to be based on your numbering convention, and it has a text field. Additional attributes can certainly be added, or properties can be added to requirements as necessary. But SysML does treat requirements fundamentally as textual rather than as some other kind of modeling paradigm. They're basically pieces of text that we need to somehow connect together and organize into specifications. And you can see that here in this requirements diagram, two packages. One package is the vehicle system specification. The other is the braking subsystem specification. The vehicle system specification includes a requirement named stopping distance, which has an ID, which has ID 10.2, and the text that says the vehicle shall stop from 60 miles per hour within 150 feet on a clean, dry surface. The braking subsystem specification has an anti-lock performance requirement, which has says something about preventing wheel lockup, and because that is really contingent on a design decision for how to meet the stopping distance requirement. We're saying in this case, you can assume in this case that this is a derived requirement, hence the derived requirement relationship. Parametrics are something that the SysML added to what UML had to offer. And in this case, it really is a way of taking systems of equations and laying them out in a manner so as to make them more reusable, and then tying those systems equations into other properties and attributes of the model. In this case, you see a parametric diagram titled that is a parametric diagram of the block straight line vehicle dynamics, which is the diagram frame, and the parametric diagram includes four separate equations: E1, E2, E3, and E4. And just like we had definition and use as shown in the structural side and to some degree on activity diagrams, you now see that same principle applied here. E1 is a constraint that invokes the constraint block braking force equation. Likewise, E2 is a constraint that invokes the constraint block acceleration equation. Those little boxes on the edges of the constraints are exposing parameters, constraint parameters, that can be wired together with binding connectors, such that we now have a system of equations that now can be used to solve for specific variables as necessary. Okay, now I want to start talking about how these various kinds of model elements can be sort of cross-connected and used more effectively, because the SysML is, or a system model in particular, is not really about diagrams. It's about the model that's behind the diagrams, and we really want to make sure that the concepts that the diagrams are expressing are actually exposing deeper relationships within the model. So I want to start with showing how some of these things can be cross-connected. Here I have an IBD that's showing the internal block diagram that is showing the traction detector and brake modulator in context of the analog controller. I'm showing an activity diagram, which you've already seen before. I'm showing a requirements diagram and a parametrics diagram, etc. The first way I want to talk about cross-connecting these kind of model elements together is with allocation. What I've done here is I've taken this activity model, which is behavior kind of unconstrained by any structural constraints. And I've now decided I want to allocate that specifically to my structure. Now, this may seem sort of trivial in this very small example to say, oh, I have an action that invokes detect loss of traction. I want to actually allocate that to a part that represents the traction detector. Yes, that's kind of trivial, and I agree. But you can quickly see that if you have a very sophisticated activity diagram with lots of things going on, then maybe that allocation is not going to be quite so simple. And so this can be a very, very powerful way of cross-connecting the behavior that you developed from a purely requirement or need-based kind of understanding of what your system was supposed to do, and now starting to allocate that behavior into the structure that you're now proposing is going to be responsible for exhibiting that kind of behavior. So when these swim lanes, or these allocate activity partitions to be more exact, are placed on top of the existing activity diagram that you'd seen previously, what it does is states that the partition or swim lane that represents the named element at the top is, that named element then has a responsibility for actually executing the behaviors within the partition. And so you can now see that D1 traction detector has the responsibility for executing, of course, A1 detect loss of traction. And of course, likewise, M1 brake modulator has the responsibility for executing A2 modulated braking force. You can see that not only on the activity model side, you can also see in the compartment notation on the IBD, the other end of that allocation relationship. It is actually a relationship that exists in the model as soon as you build the partition, the swim lanes, and can then become visible wherever those model elements are used. And so that reinforces the idea that these diagrams are not just static things. They are views into a model that is a dynamic, maturing, refining model as time goes on. The next kind of relationship I want to talk about here that cross-connects model elements is this idea of the satisfy relationship. Here, I'm showing that the anti-lock performance requirement has a satisfy relationship with the anti-lock controller as a whole. You can tell that because from one of these diagrams, from the requirements diagram in particular, because you see that there's a compartment on the anti-lock performance requirement that states such. It says that this requirement is satisfied by the block anti-lock controller, which basically means that under the covers in the tool, in the model, there is a satisfy relationship that connects this requirement to the anti-lock controller. On the IBD side of things, I've taken a kind of a shortcut. Most tools won't actually do this, but it does show a compartment notation, or excuse me, a call-out notation for the satisfies relationship, but it's tying it to the diagram frame. Now, that's a perfectly legal thing to do in SysML, but most tools aren't configured to do that. But what that is saying is that the diagram frame, which does represent the model element anti-lock controller, does satisfy the anti-lock performance requirement. Does that mean that it satisfies it in all cases? Does that mean it's proven to satisfy the requirement? Well, no, it doesn't. The satisfy relationship is basically a way of doing what we had previously called in system engineering requirements allocation. I would say the anti-lock performance requirement then becomes allocated to the anti-lock controller. Well, the satisfy relationship has that same exact meaning in that it is saying the anti-lock controller is meant to satisfy the anti-lock performance requirement. The only way we can tell if it actually has satisfied it is if we have a verify relationship to a test case that actually executes a test and collects the results and then verifies that that requirement has been in fact met. Okay, so there's a difference between satisfy and verify, and we use two different terms. We use satisfy when we're talking about requirements in this kind of relationship, and we use allocate when we're talking about other model elements. Now we're going to talk about something that's really kind of interesting and has kind of gained momentum in recent years, and that is the idea of how values and value properties of within structure can get tied into, linked into, and bound to sets of equations that you express in parametric models. And in this case, you can see that the brake modulator, in fact, one of its implied functionality here is that it applies a duty cycle to activation of the braking system, and in doing so, it has a value property, duty cycle, which has a value type of %. And so you can see on the parametric diagram, I have added a number of various properties, value properties, that I've collected from throughout this very simple model, which shows the tire friction, for example, the duty cycle of the brake modulator, some unencumbered braking force, and the mass of the vehicle, and the position of the vehicle. And I've used that to feed into the various properties, various parameters, constraint parameters of these constraints. And so we now have enough to go on here to say, well, if we have numbers for all of these things, we can start to do some calculations and maybe come to some conclusions about how this vehicle might perform. In particular, related to this whole idea of the stopping distance. The next step, of course, is to say, well, if I can calculate the vehicle's position as a function of the various other parameters on here, we can set a braking force, we can set this duty cycle, we can set the tire friction, we can establish what the initial velocity is, and then we can calculate what how long it takes for the position, for the velocity to go to 0, and then have a change in position and calculate what the stopping distance is. We would do that by specifying, in this case, an interaction, much like you saw on the state machine, much like you saw on the sequence diagram, that would say how to do that, right? And what you would set first, what signals you would expect to see go across first, what things would happen second, what is driven by what. And maybe even establish a test case that would then execute that. But in any case, this interaction then would be able to run a test, an experiment, based on the values in the model and come up to it with a conclusion of what the change in position is that would compute a minimum stopping distance. And in this case, there's an interaction that we are calling minimum stopping distance that does that calculation. And we now say that the stopping distance requirement has a compartment which says that it's verified by this interaction that computes the minimum stopping distance. So you can see how all of these parts on this very simple diagram, or this very simple example, are starting to get connected together. And so in closing, there's a lot going on in a system model that a system engineer wants to make sure is connected together and is consistent. And that's really what we're trying to get to. I mean, we could have done all these diagrams separately in a diagramming tool, in PowerPoint or Visio or whatever. But what we really want to do is to make sure that all the concepts are contained as separate entities and are connected together in meaningful ways. And so hopefully you're seeing how a system model can start to provide that continuity and that consistency, and can really aid in increasing the quality of our system engineering product.